Today my talk will be about making AI systems work for imperfect humans. It's a big topic, and we're still in the process of making a lot of the work, but it definitely is like an interesting topic, definitely that I hope to discuss with you all. So I first wanted to, before I dive into the actual work, I wanted to share a motivating anecdote that is like one of the several instance that like basically drive me to start looking into like imperfect humans, this kind of direction. I just want to say, as faculty members, we really don't like teaching really diverse courses with students with very diverse backgrounds. And as a background, I was teaching this class called Data Science for the Product Managers last spring. And this course is basically a required course for a bunch of students who want to learn a little about data science to become product managers. And because this is a data science course, all of the assignments were on some kind of data science and data analytical topics, and all of them happen on Google Colab. Basically, you have to write some Python code to go through data cleaning, exploratory data analysis, machine learning, reflection, and report on the data analysis that you have done. And because everything is on Python, it kind of require people to have some amount of coding background. And everything seems very promising, like it seems like a well-designed course. But in reality, because this is students who want to become product manager, basically they come from very different backgrounds. I had students who are already PMs but just want to learn more about management. And these kind of students usually have background in more like business side or like non-technical background. And I also have students who are pretty much just in computer science and have worked as AI prompt engineers, but have absolutely no understanding maybe in data science or maybe in like product management. And they have different technical skills, but also like their background. Some of them are in communication study and journalism. Some of them are in double E telecommunication. So it's basically everyone come in with very different level of expertise and knowledge on this topic that I'm supposed to teach. And this has historically been a super challenging course because the standard assignments is either too easy or too hard, depending on who you are. And also sometimes instructors like me, we are less experienced than a lot of students who have been in the PM role for like forever and just want to come back and then learn something about data science and like their understanding of what kind of knowledge they actually seek is very hard to predict as a faculty. And so with all of those challenges, when I took over this course from my colleagues, I started to wanted to ask, oh, can we try to make everyone's life easier by trying to create more effective or happy human AI pairs for data science tasks so that the hope is basically, so this is the environment they were trying to do the assignments in. Basically, this is Google Colab. And at this point, Colab already have Gemini natively built into it. And you have a lot of different ways to ask Gemini to do things for you in Colab. This is just a screenshot for some of those ways. So you can, on any of the coding cells, you can like do kind of natural language text to code. So basically just say, oh, I want to see the unique values in car model. And then Gemini will basically try to translate your prompt into the actual code. So that's like the coding mode. And on the side, there's also like a chat window that you can basically just ask your questions or have a chat with Gemini the same way you would chat with it in a separate window or chat with ChatGPT or chat with whatever model. So familiar interface. But the key idea here is really because you have different kind of interfaces and because models at this point are expected or we envision them to be general purpose, there is more like unlimited possibility enabled by Gemini or this kind of AI pairs. Hopefully, our ideal case would be students will be able to either ask generic questions on data science or on the domain or on stakeholders, or they can also generate code or debug. And we really hope that this will enable all the students to get the support that they need, especially for students who, like, I do not have the bandwidth to teach everyone Python 101 from the start. So hopefully maybe the model will be able to do something. And I do not understand all of the domains or stakeholders that maybe PM people will actually run into in the wild, and hopefully model will be able to provide some of those background information. So we were wondering, like, having access to AI, does it help close the gap? Can everyone get the support they need and make my life easier and also make their life easier taking this course? And we ran a study in my course basically to ask this question of like, how much do people from different backgrounds actually benefit from playing with large models in this data science task? And also, are there, if they do not benefit equally, are there ways that like some people would be able to, what are some strategic ways that allow some people to benefit more than other people? And unsurprisingly, probably like this, probably didn't need a study, I would have to predict it already. Like only some people used AI effectively. But we wanted to know like what made some people to benefit more from AI than others. Some people will be able to, even as novices, they can just ask Gemini to, through some interaction with Gemini, they were able to get really high scores, like full scores on some of the assignments even, and some people would just give up very easily. So we did some analysis on people's actual behavior. We looked into their interaction trajectory with the model and look at where they ran into challenges, when the AI solved their challenges, and when did they abandon the interaction with their original intent when the AI was not helpful. And there were a bunch of high-level observations that had. For example, data science novices usually like the idea of what kind of actions they can ask the large model to perform. For example, they do not really have clear verbs in their prompts. And whenever large model asks a clarification question, they will say like, oh, I don't know, maybe. And also some of those novices will simply just copy instructions from homework. We just see a lot of this kind of interaction, and they didn't modify anything. And depending on how well our instructions were written, there was an upper bound on how good the code they can get just by copying our instruction. And there are also students who like show better behavior. For example, for students who like do not have a plan in mind how to start an assignment or like didn't understand the field enough, they can learn progressively by asking the model to give them some guidance. Like they would ask, oh, what does data cleaning mean? And then, okay, let me instantiate all of these steps that the model gave to me onto my own data cleaning task and some kind of like learning behavior of following the model suggestion. We also saw like for programming novices, usually we expect the model to be able to explain the code that they don't understand in natural language, but they do not bother to actually try to ask the model to explain the code for them because this is probably too much cognitive load. This is a lot of detail on the actual course, but what I think our main takeaway is really interactions really matter. People are really not perfect, and we're not Oracle, and we're also not static. A lot of times, I think when we do human large model interaction, especially on the model side, we kind of expect human will be able to give the perfect instruction. Whenever model asks human a question, human will be able to give the perfect clarification question. And we expect human already know them all. We're not really changed by the interaction we're having with the model. But in reality, none of them is true. Basically, depending on what the kind of information AI will be giving to the human, they might be able to answer some questions better or worse, and they might change how much knowledge they actually have in a particular information session. For example, students might learn what is data cleaning if the model was able to explain that better at the beginning instead of just like jumping into the task. So how they do things and how AIs react change the task endpoint. And in this case, this is their grades. So jumping out from this data science, novice data science example, like but still stay in data science, I just wanted to also say interaction also really matter, even just for experts. And this is an example taken from a paper called Data Science Agent in Collab, the Future of Data Analysis in Gemini. Basically, you can imagine asking some of these end-to-end like task completion agents to go from to like just give them an instruction saying, oh, for example, I'm planning to open a coffee shop in Seattle and would like to make an informed decision on this investment using the provided data. And then the agent could do something and get really deep into the process and eventually generate you some data analysis report that's super long, hundreds of words, and more importantly, have like 700 lines of code. And if there's anything wrong, it's very hard for the human to debug at that point because you've generated too much, and even the expert won't be able to actually read the code generated by another either human being or expert and understand like exactly what's going on there and where they should do modification. Even if there's nothing wrong, it's very hard for human expert to do verification. They cannot really read the code and say, oh, this matches my intuition on how data should be cleaned in this particular way. So right now, most of our agents tend to complete analysis tasks end to end and have humans review in the end, assuming that basically the tasks will not change at all during the process, and the analysis can actually review in the end, and this actually helps save the humans' effort. But this is what we assume a helpful AI should be doing, but this is really not this is really not very helpful for the human. And usually we'll also say the agent is doing a good job if its final output is insightful. But a better way to look at this that we argue is really instead of just trying to do things end to end and give end results, we should pay more attention to the procedure. So a helpful AI should support knowledge building procedures and also do some scaffolding in the process of the actual task, especially if the task is actually evolving and it's doing a good job. If it's not only giving a pretty good output, but also the interaction process provides users the domain and also data knowledge for them to make some subsequent analysis decisions. For example, in this very particular coffee shop case, it's probably better for the agent to strategically stop and say, okay, here are some initial analysis and ask for confirmation and also ask for some additional information on the data background so that human can get more involved, model can have better assumptions on what the data is and probably make better analysis decisions. And in general, I think data science represent one kind of task that has not received a lot of attention and research. Most state-of-the-art AI would assume humans having well-defined and fixed goals. You have the goal specified at the beginning, and humans are not really changing it. You have almost a fixed environment, and the task is usually in a constrained domain, and that means you can have some predefined benchmark. But the type of task this data science task represent is really a lot more exploratory in nature. People will have more dynamic goals, and humans are learning about either the domain or skill as they are interacting with the task. And there's really no single right answer in the end that you're trying to get. Where you get in the end point depends on how you actually explore in this whole process, and that changes what kind of question you probably want to ask. So with this kind of observation on tasks, we want to ask what exactly do we expect AI to do for imperfect users in really complex tasks? Where we pretty much see that task completion should not be the sole purpose, and we should consider other more intermediate goals like maybe articulation of better sub-goals or the learning goal that humans might have, and also where many tasks really need interaction process. And you actually need human to put some effort to improve the agent's outputs because you need to give the agent more information throughout the way. And there are also knowledge work that is just by nature more iterative, and human engagement is actually part of the goal. So these days we've been working on can we assess and also plan interactions in a way that would make AIs practically useful in complex scenarios when we cannot assume static or oracle humans. And this is like a very interdisciplinary question by nature. So we have a bunch of students in our lab from very different angles working on it. Some people would publish more in the learning science literature, or some people would be more on the HCI side, more on the NLP side, more on the software engineering side. But all of us try to push forward for this goal of making AIs practically useful by mapping general purpose AIs to the right specific goals. And today I will just explain some of the work across different specific like publication domains to maybe give you an idea of how a lot of efforts can be complementary from different angles. So the first one I really want to talk about is really how do we think about the interaction process if we consider human AIs to be like an interactive um, to be in an interactive mechanism. And the paper I want to talk about is this one called Task Completion Agents Are Not Ideal Collaborators that was submitted to New York's position track, which will come out tomorrow. Basically, this is a framework on explicating the human AI interaction trajectory. So in this work, basically, we try to ask what might a process look like. The most common way that we expect humans to work with agent these days is basically a one-off task where humans give an instruction and agent will just do the job. And this allows the agents, the models to do things end to end, and their utility to the human is basically just the final output quality. But if we consider how much effort humans are putting into this process and also how much a utility agents can bring back, we can basically have like a two-dimensional graph here where we can see a lot of tasks like the one we saw before really need interaction. And ideally, we want to have this kind of linear growth where whenever people put in more effort, the agent or the model should just come back with bringing more utility to the human. And this utility could be output quality, or sometimes maybe it's like the per staff information gain, like this particular staff the agent tells you a lot more about this general task that you're in, so you can make more informed decisions on the next task. In reality, when we interact with agents these days, many of the interactions could just be futile. Like you put in more effort, the model is not really improving in any way. And this is an example taken from a paper called CoGym. And basically, this is also a data analysis task. And what the human is doing here is it realized there is something wrong in the agent's generated code, and it says like, oh, it looks like column name and this diff are not being parsed correctly, blah, blah, blah. Agents try to do something to fix this bug and they failed. And then what the human can do at this point is they didn't really have anything other than just repeating the error in a more paraphrased version of natural language and hoping that this prompt engineering will help the model do better. And eventually, I don't think they actually resolved this. But this is like one kind of really effort spent with no gain received. Like the model did not really improve anyway after the human trying multiple times to resolve this particular error. And if you keep running into this kind of interaction that's like not bringing you anything, or even like the model output is decreasing as you give more effort, it also frustrates people, and then eventually they will just drop out early. They will not continue to interact with this model. So we think like thinking about different kind of trajectories to be able to think about these kind of trajectories. Evaluation should really capture two different process dimensions on this graph. The first one is what we call scalability. Basically, do models continuously provide more utilities with additional human effort and involvement, or does it plateau at a particular point and the utility does not grow anymore? And feasibility, how much human effort models can actually get before users decide, oh, I'll just drop out. And in this framework, we argue that we want collaborative effort scaling. Basically, we want to have an evaluation framework that focuses on comparing the process of task completions based on these two different dimensions and consider both the effort and utility. And to capture things and to actually draw this figure, we definitely need human effort. And this also can be instantiated in a lot of different ways. Like it's easy to digest information given by a model at different stages. It's easy to assess the correctness of those informations produced. And it's easy to give feedback back to the AI agent and say, oh, you did wrong and you should have done it this way. Or could the model or would the human only be able to say, oh, you did something wrong and I couldn't say what's wrong. And then utility-wise, is the AI making progress to a final goal? Is it offering knowledge per step? Is human actually happy with the whole process? Those kind of questions. And utility actually incentivize human effort. Like if you have an collaborator, either human or agent, that's like continuously giving you more and more utility, giving you more and more information that you find useful, you're more likely to continuously try to interact with it. Otherwise, you will just early drop out. And both of the human effort and utility, if we actually want to consider how to quantify them, there are also a bunch of ways. For example, for human effort, we can just count the number of interactions people are having, the rounds of chats that they're having with their AI, or the context length, how many tokens they have to read, how many tokens they have to produce, information density from the AI's output, and whether the format is easy to read, is it aligned with the human expertise, and on the utility part, we can have the output performance. We can compare each two steps and say how much more information is added in this new step and whether an agent was able to answer a particular human question, all of that. And in this paper, we just did something super simple and just like said, let's try the easiest possible instantiation and just see if we can plot this kind of trajectory and whether that tells us anything. And we tried just like instantiating human effort using interaction number and also context length and utility using the output performance. And we went with this co-gym simulation. Basically, you will have a simulated human as an evaluator chatting with the agents to generate a bunch of actual interaction patterns throughout. Like I think they have travel planning, data analysis, and then tabular analysis. And TLDR is indeed we observe a lot of expected patterns in our like theoretical framework. And we can compare different agents with different prompts or different like mechanism powering their collaborative mechanism. And like, for example, on this figure, we can see like already some of the agents powered by some models have better scaling. They can better utilize the human effort, even if they started very low. For example, this blue line is cloud. At the beginning, they tend to ask the human a lot of clarification questions before jumping even at one attempt at the task. And then that makes the utility super low for human at the beginning, but eventually they tend to win. But some models, you basically just should leave them alone and just have them do their things. For example, I think GPT-4 4 Turbo, like it plateaus really quickly and then it never really improves. And those kind of models are just not as collaborative. So this does like basically things that probably you can take away from the study, how to think about the interaction process. We at least think about the process as a trajectory between the human effort and also model utility. Utility can be really broadly defined in tasks with evolving goals. Intermediate results can be a lot more valuable than a polished endpoint. And efforts should also not be blindly minimized, but should be well planned to sustain longer term gains with respect to scaling and also visibility. And the two really interact with each other. Users might easily disengage due to low utility, and AI utility only increase when they receive the right task. And more importantly, I think a lot of the time when we talk about AIs, especially agents, we try to minimize the human utility, but maybe that's not always the goal. If you actually want to push for better final task output, sometimes you actually need human involvement. And it's more about strategically plan for where should humans spend the effort so you can get longer engagement and make sure you get all the information before human decide to drop out. And with these two dimensions, now we can think about interventions. So like, what can we actually do to improve this kind of interaction process? Just looking at this graph, we already maybe have some thoughts. Like for example, you should not ask human even more questions when the utility already start to drop. You should not try to bother them. You should try to make sure you provide some value to keep human engaged. And try to do some exploration of alternative approaches. For example, when it seems like when you try to push on one particular dimension, you don't get anywhere. All of the human effort seems to just be wasted. Or like you can do exploitation if you're actually on the right track, like people seems to be benefiting by based on the current direction that you're exploring. And there are actually some theoretical grounding behind things like this. So in a paper called Principles of Mixed Initiative User Interfaces, like Eric Hoppus defined some kind of this utility function saying like sometimes it's cheaper to not act than acting on a wrong goal. And you actually want to encourage users have their own values and also their own effort, and you have to estimate what kind of action to take at a particular moment to give you better or worse longer term gain. And to do this kind of selection, one important thing is to really operationalize this notion of user more computationally, so that we can predict their goals, their utility, and also the cost of actions at different stage. I also talk about some work that we try to do in terms of try to operationalize this user more computationally. Again, based on this framework from two dimensions. The first, how to increase the utility coming from agents, and the second, how to more strategically use human effort. So for the increase of utility, I will talk a little about something we call like user-centered AI instruction following. And for that, I will mostly talk about the work that we just got into NERD. Checklists are better than reward models for aligning language models. So this is kind of motivated by this one wildly accepted form of utility, which is basically AI's following users' instructions and making sure it gives you the right answer that you're asking for. And we see this kind of patterns almost everywhere. And we also kind of engage in this kind of interaction every day. You would ask models, you would see people asking models to write stories about dinosaur or get more serious, asking about some factual information, some explanation, and sometimes also trying to trick the model to help them make decisions. And the model will refuse to do so because safety consideration is not something the model can do, those kind of things. But we ask the model to do a lot of things. But when we say instruction following, sometimes we don't consider what exactly we want the model to be doing. And this is especially true because our instruction is really convoluted. When a user say, for example, can you help me write a 150-ish word promotion text for the book, The Great Gatsby? What users actually mean is a bunch of bullet points that, like a bunch of constraints the model actually should fulfill. Like, for example, the user is actually looking for a paragraph that highlights key themes and vivid details. It should avoid major spoilers, probably because this is a promotion text. You should use engaging promotional tool, a tone, and maybe stay around 100 words. But it's probably tolerable if it's slightly longer or shorter. And some of these are very like apparent, like you already have the actual word number in it. And promotional text, you should do promotional tone. But some of them maybe are kind of implicit. Some of the models might be able to guess you don't want major spoilers. Some models probably won't be able to. So user instructions are really imperfect representations of what they actually want. And models really need to do some guessing on a missing need or on prioritization across needs and say, oh, maybe it's more important for me to highlight the key themes than trying to stay like exactly at 150 words. So one way to make it more clean is really to explicate the modular requirements that's maybe hidden from the user instruction, and try to identify any aspects of an instruction that, when absent, will cause a response to actually fail to some extent. And that's our definition for requirement in instruction. And what we want to do is really to infer a lot of requirements from failures. Basically, we want large language models to produce responses of a lot of varying quality, then prompt the large model to self-criticize the output and write a checklist of all of the possible failure modes, and then also tell us what's the weights that each requirement should be taken, how to prioritize them. So for example, generate me some quiz questions on AI agents with answers. You can directly parse them into some requirements already. Like, oh, you definitely for quiz questions, at least you need each question to have a corresponding answer. But if you look at some of the actual quiz questions generated by the AI, you can say, oh, it's wrong in this particular way, and then add a bunch of other requirements. Like if you shouldn't keep asking factual or memorization questions, because then the questions are not appropriately educational, and you should ask more about like AI in terms of like technical aspect, not just who invented OpenAI. Is too general, all of these. Key things here is criticizing candidate responses provide more coherent requirements that are not simply direct segmenting the original prompt. If you do not look at the actual arrows, sometimes the model do not get more information when you parse the original instruction into requirements. So suggest a lot of the failure modes are really hard to anticipate at a prior time. And we use all of this checklist on something we call RLCF, reinforcement learning on checklist feedback. Basically, for each instruction, we generate checklist phonetically and grade each response per checklist, and then combine grades into a single weighted checklist score, and then use the score for RL. We use DPO. A TRDR is RLCF consistently outperform other methods, and guess from arrow checklist indeed help us get a lot more information compared to just directly trying to parse checklists from the original instruction. And you get higher utility in instruction following if the model can fulfill requirements or checklists that are not too obvious from the plain instruction text. And this is one kind of workaround of humans' imperfectness in terms of cannot express ourselves really correctly in natural language. And instruction following do not just happen in natural language itself. There are a bunch of instruction following like across the pipeline of humans like interacting with kind of AI infused applications. And this is another kind of short example I want to give on instruction following in RAG pipelines. It's from a paper called Beyond Relevance, Evaluate and Improve Retrievers on Perspective Awareness. And basically, the idea here is when you have some instructions to the models that's like more information intensive, like you want to write an essay opposing some kind of claim, usually you will first go to Retriever to get some articles, relevant articles, and add them to the context window in order to actually get some like actual essay output from the large model. But Retriever themselves, usually right now, they do not do instruction following, and they can only find relevant articles. And sometimes relevance could mean that, like the stance is like even in the opposite direction of what you want. You want an essay opposing a claim. You probably will end up with articles supporting that claim, and eventually you will also have paragraphs from large models on the wrong side. It's kind of like propagating arrow. So you actually also need instruction following and your retriever part. It's not when we usually talk about instruction following, but that's also important. So what we did was basically creating something we call perspective aware retriever, try to identify really nuanced people's need in the original instruction. Like this opposing thing is really highlighted with only one word, but we want to highlight that and make sure all of the retrieved documents are ranked in a way that's aligned with what people are looking for. So eventually you can have arguments from the right side. And high utility in instruction following in this way actually also means making pipelines understand the priority by amplifying easily ignorable user needs, again, requirements and user commands. And this is imperfectness just because natural language is really unstructured. Like the instruction itself is not badly written, but like a lot of instances of dimensions that you're actually asking for is maybe really hidden in it. So take away from this two work is really we should go beyond plain text and identify and also weigh the true user needs. And on the other end, on the strategic use of effort, we also look at like jumping from user-centered AI instruction following, we go to AI-centered human assessment and also training. And for this, I first want to say a lot of like more in situ intervention can also, again, already save a lot of human effort. There has been long-standing research on AIs trying to take actions based on the user behavior. Basically, based on your current interaction, we can try to infer how to model you, and then how to understand your preference, how to understand what you will react to, like how you will react to different recommendations. Like if in Amazon, when you try to buy something, you highlight durable to pets, then it's very likely that we can infer that you probably have a cat or have a dog at home. And then like pet-friendly things, pet-friendly travels is maybe things that we can recommend to you. And we can do it in a lot of different ways. Like we can basically do, for example, in Retriever, we can, based on our understanding of human, we can do strategic inquiry to humans. This is a work again on retrieval. The idea is a lot of the questions that we ask, usually like some retriever work better than others. If your question have a lot of keywords, maybe BM25 work better, keyword-based search work better than dense retriever. But we can also consider humans as retrievers. Sometimes like information that you cannot find on the internet, you can go and ask a human, but you have to decide when to ask human, how can we ask questions that the human can actually provide value. And the way we can do it is maybe you can just model users' trustworthiness. For example, if you already observed that user have shown confusion when you previously asked about something, then like you shouldn't ask the human similar questions in this exact domain. That defines human as the retriever, and when you should query that particular retriever. So modeling of expertise helps determine when to consult human versus external sources based on their demonstrated knowledge in prior interaction. And you can also track humans' interaction behavior to say, oh, sometimes we can actually predict when people are becoming too over reliant on the model's output. Like if you keep doing copy pasting from your large model chat page to your task page without any stop reading it, then you're definitely over relying on things. And this kind of modeling of attention can also help basically prompting your AI to take some action to get the human attention back. But more importantly, this kind of short-term intervention do not really leave very, very long. It only help with one session. So we wanted to really ask, are there ways that we can also make human better? We can make human less imperfect to actually save effort across all of the sessions they engage in. And on that, I also want to briefly mention a work called What Should We Engineer in Prompts? Training Humans in Requirement-Driven Use, Large Model Use. Basically, it's a work asking what should users do effectively to make AIs work. So what skills make AI used more efficiently? It's like a big debate in learning science in all of the education domains and across HCI. But one thing that we also like get in is really observing how we're spending efforts when we are interacting with AIs these days. We iterate on our prompts. It's either through just iterating and editing your one particular prompt, or in a chat you would say like, oh, this is too long, blah, 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 add additional, like try to have back and forth with the model. Eventually, what you are doing, if we still take the requirement kind of view, is really clarifying from an initial set of requirements to the end of requirements, and also like express those requirements in a way that the AI can understand to fulfill. So people would need to spend less effort if they could express what they actually want more easily upfront, if we can reduce the number of iterations or chat that they have to go through. And one important skill for future of work is really, can people write requirements more efficiently so that models have an easier time guessing what's missing from your requirement. And also models can do some guessing. They cannot do all the guessing. If you're missing requirements that's deviating from their training defaults, they won't be able to guess what you actually want. So we created like a training mechanism that we call requirement focused training. Basically, in this training suite, we have students try to learn how to enumerate their requirements comprehensively and precisely by having them practice replicating existing programs. These programs are either GPTs tasks, like the apps on GPT store where other people have written prompts that have requirements in it that like make GPT into a particular app, like travel agent, or also some kind of like more interactive game tasks that's more traditional software engineering, because this whole requirement elicitation actually is a taxonomy and a framework that's widely used just in software engineering. And what they do is basically to replicate programs by enumerating all of the requirements that is in that program. And they don't need to write any code. They just need to arrive at the requirements. And the way to arrive at the requirements is basically have a chat with like a large model simulated tutor that gives them feedback on their identified requirements. The core mechanism is we try to give deliberate practice with automated feedback on just the requirements. So people do not write prompts and they do not directly talk to large model to generate this program, but they talk to a tutor in a like really unstructured way to say these are some kind of requirements that I think I observed, and the model will be able to structure it and generate the final code based on the formalized list of requirements. So it will give feedback on learners' input requirements. It will summarize learners' stated requirements into a list. It's basically something called worked example in learning science way. Like it says by showing students how their requirements can be written in a really formal way, students will also learn how to write things more structurally. And then eventually, using this structured list of requirements, the system will try to produce like a replicated program for students to understand what replication failed, where replication succeeded. And this failure is basically their missing of requirement. It has nothing to do with whether they wrote their prompt correctly or not. And eventually, we also defined assessment for the students, basically, again, having them replicate some kind of prompt programs by looking at some actual chats people have with, for example, a travel advisor to reverse engineer what kind of requirements was there. And even though in their training, we didn't have them write prompts, in the actual development, we do have them like write the prompts. And we evaluate both in their prompt whether they hit the right requirement, and then also whether their actual large model output is correct or not. And the way we want to do this is an assessment in this way is really want to give like understand, do people still remember about the requirement and can apply them when they go back to writing really unstructured prompts in the wild. TLDR is this training that's transferred. Basically, it helps novices better instruct models. They naturally start to use requirements in prompts to avoid confusing AIs by giving too much information, and to also organize prompts parts logically for easier revision. And this is not something you just get from interacting with the model in the wild or just watching a video. And again, this is like kind of a utility problem. Large model itself cannot really provide focused reward on students writing the right requirements, because even though you have all the requirements in your prompt, maybe the model get confused because like it didn't understand a particular paraphrase that you used in your prompt, didn't understand a particular grammar. There are too many sensitivity in the prompt. But like when we structure things in a way that says student only need to hit to the right requirement, and then once you hit the right requirement, it will definitely give students the right program. It helps them to observe the direct impact of the requirement, and people start to actually learn more about that. So longer term explicit interventions are necessary, and they exist in the form of maybe education related design in the future. So for this, to enable AI-centered human assessment and training, it's probably really important to have a balance of local decisions and also global trajectory. And it's like important to do both short-term user modeling and probably also longer-term training. And I intentionally had this to be like contrastive writing, like user-centered AI and AI-centered human, to really highlight that it is maybe feasible and also valuable to try deeper integration of human and AI. And inference time could be effective already, but training could be more fundamental and more lasting. And it's still open question on how and also what to train on both the human and AI side. But it's really important to know that we should focus on both sides, like both making the AI better, but also make the human better. And it's also important to think about utility and effort together better. Right now, we are basically just like looking at individual, either increasing the utility or decreasing effort. So it's still open question there. But with that, if you have like if you want a one slide takeaway from all the talk of all the questions we asked and then one sentence answer, this would be it. And I'm happy to answer any questions that people might have. Thank you so much for listening.